this is what we are talking about today. Timber structure 3, columns, slabs, ready. I'm an experienced timber engineer. We did in my company Timbatec about 3,300 projects so far, and many more to come. And we always have the same challenges in timber construction. And the main challenge is timber is just unaxial load bearing. As you see on the left-hand side with these arrows, red and green arrows, you always think as an engineer, first, where can I put my beams? Where can I transfer my loads into vertical elements like columns or walls? And on the right-hand side, you see what it looks like on building site. You always have beams, and this is a major restriction. Yeah, see here. It looks from the inside quite nice, but underneath of the slab, you can see this is what I call our challenge number 2. These beams which interrupt mechanical installations. So with any mechanical installation, you have to transfer through the beams, and you have to either make the beams much stronger than it would be needed normally, or you have to reinforce them. And some public bodies demand that you make at least 30% additional space for mechanical installations. So I'm going to ask you, where do you want to put these 30% in addition if you don't know where they have to be? You will have probably the wrong place, the wrong diameter, the wrong slope. So it's actually something which we face every day in our engineers' work. What is also, if we look at the time we need or we use to construct buildings, we use something like 10 or 20% for the main structure, and about 80% to 90% for these hassles we have to challenge these mechanical installations and all these special cases which are not going to the main structure. And then third challenge we have, as we face that in Europe, or especially in Switzerland, we have a mix of materials, which is mainly steel, timber, concrete. To get rid of these beams which come out of the slabs, we replace the wooden beams by steel beams, and to tackle the fire protection and also vibration issues, we add a layer of concrete on top of each wooden floor. So we have a complete mix. And it was maybe 10 years ago, as I said, this cannot be the final solution for timber construction, especially for multi-story buildings. This is not timber construction. This is something strange. And then the fourth challenge, there are already buildings being built just in a column and slab system. This is, you might know this, for our Commons building in Vancouver. There was also a Swiss engineer, Bernard Gaffner, a very skilled and smart engineer. And he had to deal with things with the toolbox he has got. So this is already quite close to that, what I'm going to present you today, but they have just the edges of the CLT beams, which they can support. So the column grid is about 2.80 meters by 4.50 meters. So you can use that for a student home, but not for flexible use like offices or other uses. Okay, this is what the timber construction can offer, and the market wants something different. The market wants buildings with a high flexibility of use. So the top left picture shows you a demand which we are facing very often. Buildings with something like 30 by 60 meters, with several stories, 4 to 6 stories, often up to 8, but sometimes also into the high-rise, mid-rise, high-rise region. If you do it as you do today, on the top right, you can see there is a forest of columns. There are high beams, and the building is being higher than really necessarily used, and you're building a lot of space which you cannot use. On the bottom left, you can keep the height, which is good, but it's made with a CLT walls, varying wall system. So there you have no flexibility at all because all the walls are load bearing. You cannot remove one of the walls. And what we all would like to see is something like on the bottom right, very few columns and a limited height, which can also be achieved by timber construction. For comparison, that's what our market partners do with concrete. They do reinforced concrete flat slabs. They do it all the time. And we said we want to do the same. But what exactly is the same? What exactly did we want to achieve? So we said we created what avenir, it's in French, means future box. What is our future box? What are the requirements on this future box? We said on first time, we have a column grid of 8 by 8 meter. Why 8 by 8 meter? It's because of the parking in the basement. 3 cars beside each other gives about 8 by 8 meters. We noticed in the last months and 2 or 3 years that it has to be slightly bigger. So we go into 850 to 9 by 9 meters. And then it also has to provide a life load of 5 kilonewton, which is 500 kilo per square meter. But living, there is just 200, or office is 300. So life load 500, and we have much more flexibility of using these rooms. Should be flat slabs, no beams underneath, no beams on the top. Therefore, it should be point supported and multi-axial load bearing. And in the end, it should be timber only, no steel and no concrete. So the first thing we had to develop was a column head. The high loads in the panel, which have to be transferred into the column, and they require a special column head. We developed very, very strong column heads made of beech, veneer, plywood, and we noticed in the end, it's not necessary. In the most cases, in the very most cases, and just a CLT panel is sufficient up to 40 or 50 tons. And this is in the most cases sufficient. If we need more, we have a very wide toolbox with different types of column heads, which are especially for the inner columns to be used. This was the first part. We were very afraid of this. And after about 2 or 3 years of research, we noticed it's possible. And we also drilled a hole to transfer the loads from the upper stories down to the lower stories without affecting the panel, the slab panel. So the second question was how to connect these elements to each other. As soon as we have the columns, we have the column heads. How do we add the rest of the slab to these column heads? We ended up developing a butt joint connection, which is not only strong and reliable, which is also suitable for building site application. So we have to do that on building site. Why this? The elements which are be transported have the size of a truck. That means 2.5 meters wide, and the length of a truck, which is something like up to 12 meters or 15 meters, but not wider. So we need to connect these elements on building site and not in the factory. We developed We developed the butt joint connection. We started first with finger joints, which draw back from the joint, and with a distance between the joint and we thought we must have something strong to just fill in. This was the first thought. Then the rupture was always on the end of the finger joints. So we noticed, we asked ourselves, is it possible to completely remove the finger joints and just make a butt joint? We tested this and found out, yes, it's possible. And on building site, it's done with a special gear, special equipment, like a 2-component polyurethane adhesive. So with this, we took the solutions, or the good part of each word, the timber part, which means fast, dry, lightweight, clean, and carbon storing. And from the concrete side, we took the white column grid and the flat slabs, and we connected it to a new system. Here we go. I missed this slide. Okay, let's see the starting point. We started with these finger joints, and we said we shouldn't be forced to slide in on building site these heavy elements hanging on a crane. We cannot go into finger joints because there always will be sort of slightly deformed or destroyed, and we won't bring this stuff together. So we have to keep them apart and just fill them up with a strong material. We made first tests. Now you see on the right hand side, it's 20.3 down to 18.8 Newton per square millimeter, which means megapascal, which some of you might be more familiar with. And we noticed, as I said before, the rupture was always at the end of the fingers, at the finger joints. So we asked ourselves, do we need these finger joints? And we tried without. And we noticed on the bottom right, you see the 2 red bars. We are lower, but not that much lower. We are still in the same region. And we said, if we do more research about this, we might achieve the same values without finger joints. And then we would end up having a CLT panel, or what panel ever, just cut in rectangular pieces without any machining and any further machining, and we could join them on building site. So we did lots of research. And this is just to show, you don't have to see all the numbers. You just see on the left-hand side the megapascal, which we achieved, and on the bottom, many different ways of connecting. We tested a lot of different materials, also a lot of different adhesives and or casting resins. And we also tested building site circumstances like hot, cold, wind, sunshine, dust, oil, water, what all these conditions you have on building site. And out of this, we also developed a quality assurance system so that we can provide a certain quality and also reliability on building site. Meanwhile, we did about 10 years of research, more than 3,000 tests for this connection. So we know pretty much what we do the right way, and much more to which wrong way not to do. So there is very few ways to do it the correct way, so that we can provide always a certain quality of the joint. Next question was, how will it behave in fire? We did some small fire tests. You see 4 glue lines on this small piece. It was just to see if the adhesive will explode, will drip out, however it will behave after 30 or 60 minutes. And you see in the middle picture, you see these like little mountains, and there is at the joint, it's burning slower. The burning rate is smaller than on the wood itself. So that means for us, if you can deal with the wood, you can also deal with the joint. Now, this was the small test. What about the large test? What about the fire under load? We did also large fire tests. We had a standard test in Switzerland, which is a span of 5.3 meters, panel thickness of 20 centimeters, 200 millimeters, and a load of 3.2 ton. And we made a certain ISO curve of temperature, and we had a failure after 69 minutes. Okay, now we said we did quite an interesting system, and we called it TS3. Why TS3? We said it's a third generation of timber construction. First generation is you cut the tree, you chop up the branches and the tree tops, and you use it as round wood or rectangular wood, sawn wood in buildings. First generation. The second generation is we slice the logs into pieces, into boards, lamellas, and reconnected them as glulam or CLT, as you all know. And the third generation, we said, it's a connection, end of grain, a butt joint connection, which opens you a very vast field of new applications. So you can use this, as we started in the beginning, to a column grid of 8 by 8 meter, to a live load up to 500 kilo square meters. It's columns, slabs ready. And it's really possible. And I think at this point, it's very good to talk about how to develop things. If you have a factory who produces whatever, particle board, plywood, the CLT, you have this factory, you have to fill this factory with contracts, and you have to sell what you produce. And then you always have to think, what can I do with my material that I'm producing? Me as an engineer, I'm completely free. I don't have to think from the start. What do I have? What can I do with it? But I can think from the end, from the goal. What would be good? What would be necessary? What would be the requirement which the clients want from us? And how do I get there? And this is much easier for me now because I'm completely free and I can collaborate with whoever I want with. That doesn't mean that I would be better or worse than anybody else, but it's just the situation I am in. I'm much more free to develop things, and I don't have to look after a factory or employees who have to be employed every day to keep kept busy. I can just develop and then find my partners and develop from the end, not from the start. Okay, what else can I do? I can do slim slabs for high-rise buildings. So that means in a high-rise building, it either is lower than normal with timber construction, or I can add more stories in the same height. And the panel doesn't care, because the weight, the load, you can see here, the load of the upper stories is transmitted through that drilled hole. So I don't affect the panel with the higher loads. And the only task is to bring these loads through this hole down to the next column. And the column, best you do it in wood, but it doesn't necessarily have to be in wood. Sometimes, especially in the lower stories, if you make very high rise, it's also feasible to do them in concrete or steel concrete connected, or steel, however you want. It's also possible to make rigid diaphragm walls, which we couldn't do so far with wood because it was always too soft. And this is, I think that this was the main application. Now there are some fancy applications in addition, which is also thinkable. For example, you don't have to connect straight parts. You can also connect folded parts, like for example for folded structures, or for boxes, like box hotels without any frame at the window. We just have a frame which is rigidly connected, a wall to a floor. The only thing is, let's see here, always take care that the same layer is going around the corner. As soon as you mix the layers so that a length and a rectangular parallel and a T-wise connection exists, then it doesn't work. It always have to be lengthwise to lengthwise connection. There's even more fancy stuff. You can do complex folded structures like a turtle-shaped roof, things like that. And there is one more I will show you later on, where you really see which is possible to do very, very complex folded structures. And now it's even more fancy if you find somebody who does curved CLT in one or two directions. We are always able to connect these, so you can do any shape you can imagine coming out of the nature, whatever, like eggshell or things like that. You're always able to connect these with the TS3 technology. Like you see on the top right, just take care that you can cut it into parts which are about the width of a truck, which means 2.5 meters wide, and the length which is suitable for a truck. Okay. So then we find out, yeah, now we have a nice system, we have a nice name. How do we sell these, and how do we manage these? So we founded a new company in 2014, which is called Timbagroup 3 AG, Aktiengesellschaft. Meanwhile, we have 10 employees. Pretty fast development. So the last, I don't have proper pictures, but still you see there is quite a few persons working with us. And on the bottom right, you see 2 PhD students which do further research, especially in terms of lightweight panels, not CLT panels, but something we call the grid box, which is a box with a grid inside and a lot of air inside. And we do also some more research about the joints, especially in harsh weather conditions like cold, ice, and things like that. We integrated this company into my Timbagroup Holding. It's my company, where also Timbatec Switzerland and Austria is already in. So Timbastructure 3 is also part of this Timbagroup Holding, where we are about 60 employees in the whole group. Okay, you might ask, did you do already any buildings, any projects, or you're just researching? No, we are also building already. We had about 20 projects so far, which is close to 10,000 square meters or 100,000 square feet. We have another 8 contracts. The projects are getting bigger. And we have a large pipeline of about 50 projects, more than 200,000 square meters, which are asked. We won't do all of them, but we hopefully do many of them, of these projects. And I would like to show you some of the projects we already did. We did projects in Switzerland, Austria, Canada, and the US. Most are in Switzerland because I can take some out of the projects we do with Timbatec engineers. We're just asking, Stefan, can you help me? We have a certain project, and of course we try to help, and sometimes it really works good. Sometimes we fall out of the competition, yeah, and they find another solution. Okay. Now let me show you a certain project we did to, on one hand, research, do more research, on the other hand, also demonstrate. This was in inner court of BFH in Biel. It was there for 3 years. Now it's teared down because we are preparing a new piece, a showpiece, which will be ready in next May in with the International Timber Bridges Conference in Biel. This piece was a building of about 8 by 8 meters, sitting just on 4 spots. You see it on the right-hand side, these little yellow spots. And it's basically the panel on the bottom, which is important. The rest is more showpiece, but the basic panel consisting of 8 CLT panels, which are, the blue line is the glue line, which are consisting of connected CLT panels. And on top, there is rocks sitting on top of this panel. It was also a showpiece to show to everybody, no, it's not sort of, don't ask me, undefined bags or whatever, but everybody could see these are rocks. And this was very important to build trust by the planners and engineers and architects. We had 12 tons of rocks, and this was sitting on top of it, so everybody could see, yeah, this is reliable for a long time. The wall and the roof is also connected with TS3 joints, the roof in a sort of turtle-shaped triangle roof. Then we got into commercial applications. This was a 4 residential multifamily building, 5 apartments each, so 20 apartments in all, a little more than 2,100 square meters. You can also see on the right-hand side where the panels are connected and with a certain very, very few columns hold, so that you have a big flexibility to remove inner walls if you want. Some more pictures about this project. It can rain. It's possible that it rains while you're erecting the building. Better not, but very often we do have rain, so it's possible. Just be sure that the joint is covered by a special tape, which also is sticking if it's wet or slightly wet, and the joint can dry out. And then you saw this picture before. We add this 2-component adhesive, which is delivered by Henkel, by the way. Now this is what it looks on the inside. Apartments, flat slab, no beams. And then one more project. Hang on. No, it's this one. One more project. You saw that picture before. Is a roof of a shop in Austria, a column grid of 7 by 7 meters. And the special thing is, on top of this roof, it's possible to add more stories, which is also planned. They plan to add some 2 stories later on, and the roof turns into a slab. And you don't have to care about the load, because the load of the upper floors just goes through the panel, through these columns which are already there. Unfortunately, I have no better picture, so you have to see this picture with this plastic around the columns. And this was the largest panel we did so far. It's a 650 square meter CLT panel. So it's the largest CLT panel in the world, but actually it's not difficult to make a bigger one. Just add some more panels and connect them by TS3 joints. Yeah, then this is a smaller building. It's actually my own building. I'm living here since 3 months now. We did there some more tryouts. We also did the basement in wood. So there is no concrete on this building. There's just wood, also in the basement. You can see the panel size. It's about 8 by 26 meters. We made a flat ground, some insulation on the bottom of the basement, And then we added the timber basement. And it's an entire box connected TS3 casting connection. And it's a stiff box inside it all. You can see on the inside, on the left-hand side, there is a room, a common room of about 60 square meter. On the right-hand side, there are the apartments. On the roof or on the ceiling, you can see it's slightly reddish. This is because it's beech wood. We tried to connect beech wood, which works quite well. Okay, then we have a 4-story residential building, Frankendorf, also Switzerland, 1,800 square meter. Some impressions from the building site. Here you see a special task which we can deal. You have the column in the corner, and the slab is running from the inside through the outside without any interruption. This is possible also from the building physics, point of view of building physics. And you might get an impression how easy it is to work with TS3, round columns, and any parts of the building which sticking out from the inside to the outside, from the cold to the warm. This is not the biggest, but in my opinion, the most beautiful we did so far. It's a roof with a very free shape of the corner. It's actually a flat roof. It looks slightly rounded, but it's not round. It's absolutely flat. And this is just a roof of close to a lake, of the entrance to a lake with a restaurant, which is covered. And it could be also the first floor of a mid-rise or high-rise building, because the panel, as I said before, doesn't care about the forces which go through these pinched holes. On the inside, once more, you just see a wooden surface from underneath, absolutely flat. Nobody cares of beams, and you can use the walls inside, non-bearing walls wherever you want. This is a building. I don't have pictures so far, but it's being installed. It's an office building in Vancouver, Canada. It's a building of Robert Malczyk. You might know him. He's our hub in North America. So if you have questions about TS3 in North America, please refer to Robert Malczyk. He has his own company, timberengineering.ca. He's not with Equilibrium anymore. His own company now. Okay, we have a lot of contracts and preparation of contracts. And this is the picture I wanted to show you before. This is a very complex folded structure, like a plant structure. And the very important thing is here, if you do things like that, you should do it with us. Don't do it alone, because there are so many things we can do wrong. And you see these little black stripes. This is the grain direction of the covering layer. And it's very important to have to notice where this grain direction goes, because you always have to meet the grain direction of the neighbor element. Otherwise, it won't transfer loads. And we did a special program, especially for this task, because we really had to find the right angle for each and every part of the building. Well, there is a vast pipeline, 200,000 square meters of buildings. And now I'm coming close to an end. We're talking about license system. We spent a lot of money, about $10 million so far. How do we get this money back and eventually a little more so that we can keep on developing? And also, how do we manage that it's really a safe and a high quality process and a high quality product in the end? We decided to do that with a license system. So we have several involved companies. And first, it's a CLT manufacturer. Our main CLT manufacturer is Schilliger. It's the biggest CLT manufacturer in Switzerland. We have Henkel, which produces the adhesive, the casting resin. We have civil engineers, and we have a building contractor. And in the end, we have an adhesive specialist, an adhesive application technology specialist, which at the moment, in most cases, is TS3. Okay, it's ourselves, but we give licenses. So on the top, on the right-hand side, you can see what we are trying to reach, which situation. With TS3, we want to do things which we can better than anybody else, and all the rest, especially things which have to be done in place, have to be done by license holders. So TS3 does the research and development, of course. We do patents, application, and licensing, and keep the patents up. We do training, we do marketing, and we do project management for the projects we do by ourselves. And all the rest we give out to license holders, which is mainly engineering, production of CLT, the adhesive or casting resin production. Transport and assembly is not a license. This is actually not quite in the right place here, because for transporting elements, you don't need a license. And for the assembly, for the installation of the elements, also not, so that the timber builder doesn't need a license. But for the application technology of the casting resin, there is a license needed, and also the quality assurance of the whole process. And you see the green rectangles. In the green rectangles, there is written who is going to pay these license fees. It's mainly the CLT manufacturer, because the CLT manufacturers have to do a process inside the factory. They have to prepare, to pre-treat these edges of the panels, which turns a normal CLT panel into a TS3 panel, which has to follow according to plan, which also have to be controlled by the engineer. We have also the adhesive producer, the casting resin producer, who does pay a license. Then we have the civil engineers. You see the dollar sign is very small, so they're not have to pay much, but we want to have the engineers to be trained. We also did a training in Moodle Cloud, so that all the engineers who are interested can send us an email. We can open the Moodle Cloud for them, and they can learn how to plan, to design TS3 elements. And in the end, we have the adhesive specialist, which also is a very important part, or plays an important role in the whole process. Okay, and that's it. Thank you very much for joining, and now I'm open for questions.
Okay, Stefan, thank you. Congratulations, that was an excellent presentation, an interesting system, and I agree with most of what you're saying about this flat plate system. It seems to be the future. So well done. And we've got a number of questions. So let's start with from the top. The one from Hope, it was, what is the floor panel thickness and what's the size of the column? I think it was one of your very early building designs.
Yeah, let me show you again my screen. Hang on. You can go to our website. On the website, TS3.bits is a TS3 configurator. You might see this. Yeah, exactly this one. There's a configurator. There you can choose English on top left. And then you can enter the span, like for example, 6 by 6 meters. And the live load, let's say 3 kilonewton. And then on the bottom, you see the thickness of the layers, the thickness of the CLT panel. You see also the price indication, which is prices from Switzerland. Maybe in your country they are slightly different, but in general you can see more or less what you have to calculate. And this build-up, floor construction build-up, is also to reach minimum sound insulation performance between two apartments. So for Switzerland, it works. For your country, maybe you have different regulations. Have a close look to this, but usually it will work. And you can also tip this, you see that, this piece, what is it, checkbox, yeah, with or without floor construction. So that means this is for certain industrial, commercial, where there you don't have any sound protection or sound insulation requirements. If you do have, just click this checkbox and everything will be slightly thicker. So, and you can also see on the bottom right the deflection picture and the maximum deflection with creep in millimeters, so that you can see if that works with your inner walls or windows, whatever.
Excellent. Thanks, Stefan. Another question, Salvatore. He wants to know a little bit about the earthquake conditions. Has it been tested for earthquakes?
No, but actually it doesn't help much. We have the same stiffness as a CLT panel, so you can calculate in terms of stiffness of a rigid panel, but we didn't do any earthquake research so far.
But the system would have a very good diaphragm moment transfer at the joints, so it may be better than a traditional CLT floor system. So
I'm not so sure.
Okay.
I think it's really rigid, so you cannot dissipate any forces of earthquake. You would have to add any means like the softer steel brackets, whatever systems exist in the world. You have to see a CLT a TS3 panel just as an entire large
diaphragm
CLT panel.
Yep, excellent. And the New Zealanders have got an excellent earthquake resistant system that could be incorporated. So Nicholas has asked a question to me: what is the design life of these TS3 systems building? How long will they last for?
Design life.
Design. How long? What's the life of the building?
We don't have any designed lifetime. It just you erect it and it stays there forever. So there is no reason that it should have an end of life.
So it's no different to a traditional timber building. Excellent. That's, that'll do. Hope again has asked, what's the vibration? Is the vibration design for this? How do you overcome vibration issues?
The vibration.
Vibrations would be the floor vibrations. Sorry.
Yeah. I understand. But is vibration for sound impact, right? Or for
more for footfall and just
footfall.
For occupation vibration.
So it's same as CLT. You can calculate the whole panel as one CLT panel.
Okay. And punching shear as well. How's punching shear, which would be the floor plate to the column, is dealt with?
Yeah. In terms of punching shear, we did a lot of calculation. We found out it won't work. It won't work if you calculated it the way you did before. So we did a lot of tests, and we found out these punching shear values we have in our codes are much too low. It has to do, on one hand, with a lot of reserve factors, and on the other hand, we noticed when we did tests, with just punching tests like 2.5 by 2.5 meters square piece, and we are punching through with a hydraulic cylinder, we found out that we have a rupture inside this structure, but it still works. You don't hear it, you don't see it, you don't notice it. There even is not much deformation, so you cannot calculate by punching shear values which you have in the codes, but you have to accord to the values we found out in our tests. So we make the the design by punching force through certain diameter, certain thickness, certain layers, layup of the CLT panels. I know it sounds strange, but I'm an engineer, so I'm used to work with codes. And you just, in this case, the codes, the punching share codes, also rolling share values from the codes are not suitable for this part, this way of forces.
Yeah, I probably agree. I've been doing some work on roll and shear, and it's different to what we find what the European Eurocode has. Our wood here is very knotty, so it doesn't get as much, doesn't behave as much similar, behaves differently to what the European does. So it's interesting. So I suspect the engineer who is a license holder would be able to get this information. So so anybody who wants to take on a license, they'll get that information to help them with calculating the punching shear. So I'll just move on. Yeah. There's a question about fire. Why was the fire test done for 60 minutes only? And I'll probably just jump into that one because I'll answer that one. And I know where it was coming from. In Australia, we have higher fire resistance levels, so time periods. So we can go 90 to 2 hours. You know, in the rest of the world, 60 is quite a common fire resistance time period. So that's the reason why I've done 60 minutes. Just as a common period. Yeah, obviously you can go higher by having a thicker floor or adding insulation panels to the underside of the floor and things like that. So it's just so you're testing the adhesive joint, not the CLT floor system.
And it's an exposed adhesive joint. Yep. It's exposed to the fire. So anything, if you cover it, you can get much more a higher fire resistance. But it's not limited to 60 minutes. It was just one test we did. Yep. So we know that it works, but we can, as you said, Andrew, we can do much thicker panels, and then we can go up to 200, 120, 180, 240 minutes.
Yep.
That's no problem.
Excellent. And just dial that up to whatever is required. Salvatore's got another question. What's the weather conditions that are required for optimal efficacy for the glue joints? So is there any limits to where you can glue the joints? The weather conditions.
Let me say that in general. The harsher the weather, the more complicated the things you have to do to achieve the certain safety of the joint. So we don't have actually weather conditions which we define. If it's wet, you have to dry it first, so there should be no water at all in the joint. If it's too cold, the adhesive we use needs to have something like 17 degrees Celsius. So we experimented different times, and we do have experience with heating up the joint by wires. And you must know that the joint on building site is just between pre-treatment on one side and pre-treatment on the other side. So we are not connecting woods. We add pre-treatment on the edge of the wood in the factory. So the pre-treatment is also a two-component polyurethane adhesive, and we are connecting just the tube layers of pre-treatment to each other. So we are not necessarily depending on a certain wood moisture, for example.
So it's an adhesive to adhesive connection, not adhesive to wood occurring on site. So it's more controllable. So move on. We've got a couple of minutes of questions. Mike wants to know, is there any mechanical fasteners at all in the bond of connection? And I'm going to add to that question. You know, I've seen it, talked to you before, where you've used a spacer, X-fit spacer in the system to draw the panels to a certain dimension. So that's the only fixing I've seen. So you can comment on that?
Yes, we do use X-fix. They are not strong enough to really keep the panels together if the joint would fail, because the X-fix has something like 2 or 5% of the strength of the whole glue joint. We do, in certain cases, we do crosses of full threaded screws. And the X-fix is more like, as it says, it's to fix the panels to a certain distance to each other on building site while erecting, which is very, very easy to use. It's very fast and good. And I don't know, not mistake proof. I don't know if it's the right word. You can really put the panels together, put this X-fix in, and it's very fast.
Yep. Yep, it draws it together. It's X-fix, for people who don't know, is that LVL bow tie arrangement where you use a sledgehammer to drive home just to draw it together. So it's quite an interesting way of joining the panels together. So we're just about running out of time.
It's actually not LVL. It's a plywood. Plywood. So rectangular. Yeah.
We call plywood cross-banded LVL. So it's
cross-banded. Okay.
So just being a bit facetious there. So. So we've got one more question. Okay, so it's really a question, how would someone in Australia get hold of this technology? So what would be the next step? What would they do to get a building built or look at a design?
Yeah, as I said before, there are three types of licenses. One is the CLT producer, one is for the engineer, and one is for the application technologist. So just get in contact with us, and we are happy to serve you with all you need.
So most of the people on this webinar are either engineers or building type people, so the building professionals. So they would be the engineers would contact you and get a hold of the license for a small fee, and you'll be able to help them. So with the presentation, we'll give you. You're happy to give your contact details out?
Yeah, sure.
Okay. All right. Well, thank you, Stefan. What we'll do now is wrap up on the presentation, and so I'll just get back to our presentation. So we're coming to the end of our talk, and we have just a reminder about the CPD certificates. So they'll be sent to you at the end within the week of this presentation. Please keep them for your own use. Just a reminder of the questions. Name one reason why the beam cause issues in the mass timber buildings. Obviously, jumping to if you want to know the answer, it's going to interfere with all the services, and also increases the height of the building, allows you to do more floors in the building, or reduce the height of the building. What are the CLT panels joined with? Obviously, that's the main talk about that. They're using the epoxy adhesive, two-back epoxy adhesive.
That's polyurethane glue, or polyurethane, not epoxy.
Oh. Okay, sorry.
Polyurethane adhesive.
And what is the maximum grid spacing proposed? So your presentation talked about 8 by 8, but you also alluded to that you've pushed them out to accommodate for the big American cars, which are 9 by 9. Is that the case?
Yeah.
Excellent.
Yeah. Sure.
And just a bit of a sideline for this one. We're also doing a project on this one. So my company is looking at modelling systems like this. So we've got looking at the post and plate systems, and we're looking at 3 systems: an edge, corner, or centre supported post, similar to what we just saw with Stefan. A Rotherblast, pillar, and spider, and X-Lam also have a band beam system. So we're currently investigating that. And if you're looking to get more involved or know what's happening in this one, just email me, and I'll be able to involve you. So we're trying to virtually model these buildings to work out a construction technique which suits the Australian conditions. And which is important then, so that it can, as we able to help the suppliers of these systems be able to get into the marketplace. So with that point, I'd like to remind you of our next fortnight webinar is on the 26th of October. It will be back at 11 AM on a Tuesday, and it's Beyond Zero, Maternity Life Residential Case Study, presented with Theodore Curlis, and finally, his building has got up. So I'm very pleased to see that. See the case study for this building. So for information, Wood Solutions has this in focus, and that allows you to download some or view some videos. And there's 3 videos which are on show is how is laminated veneer lumber made, and how is cross-laminated timber made, and foundations of acoustic design. So I recommend it because I've looked at these ones; they're very interesting. I actually learned something myself while viewing them, so I highly recommend them. So at that point in time, I'd like to, it's now slightly after 4 o'clock, is to say thank you and to thank Stefan for his time. It's very early in the morning in Switzerland, so much appreciated for him getting up early to address this webinar. So we'll see you all at the next webinar. Thank you.